Let's look at some more examples of some trig identities, but this time we're going to also, or mostly, focus on examples that use secant and tangent instead of sines and cosines. And so before we get into those, we want to just go through a couple of facts about trig identities using secant and tangent. First, remember that the derivative of tangent is secant squared. I'm not going to prove these, but this we can just get by writing tangent as sine over cosine, take the derivative using the quotient rule. We also need to remember that the derivative of secant x is secant x tangent x. Again, write secant as 1 over cosine, take the derivative, and it simplifies to secant x tan x. We also need to know and remember that if we start with 1 plus tan squared, we end up getting secant squared. This is essentially a reworking of sine squared plus cosine squared equals 1. If we take that and divide by cosine squared, we end up getting sine squared over cosine squared, which is tangent, cosine squared over cosine squared, which is 1, and 1 over cosine squared, which is secant squared. But in the end, let's we can use these trig identities, these trig facts, in a similar way. It's a bit more complicated than what we saw in the sines and cosines, just because the derivatives are a bit more complicated, but the ideas are basically the same. So let's look at a few examples. Because 1 plus tan squared is equal to secant squared, we can always turn secant squareds into tangent squareds, and we can go the other way, turn tangent squareds into secant squareds. Because the derivative of tangent is secant squared, if we end up having a secant squared and then any power of tangents, then we can make a substitution to turn this, I have the tangent and then the derivative of tangent. So if I had tangent to any power, tan 6x, we can make a u substitution where if u is tan x, then this becomes u to the 6th. Derivative of tangent is secant squared, so it would become u to the 6th du. So this stuff is du, and we get u to the 6th du, which is u to the 7 over 7, which is tan 7x over 7 plus c. So this idea, if I have two secants and any number of tangents, then I can use this idea. So if I have two secants that I can use, and then I can turn everything else into tangents, then we can apply the same idea. So for example, suppose that I had secant to the 4th x tan cubed x. In these first examples, it really doesn't matter about the exponent on tangent. Essentially, if we have an even power of secant, if I have an even power of secant and anything over with tangent, watch what happens. I'm going to save two secants. I'm going to save two of them. I'm going to write the other two separately. And then because 1 plus tan squared is secant squared, I can turn these other secants into tangent using that formula. And we have secant squared x. This is 1 plus tan squared, tan cubed. Remember, we're saving this because it's the derivative of tangent. That's 1 plus. So now if I write that as secant squared x, distribute this tan cubed in, I get tan cubed x plus tan 5x. And finally, using the idea that we just saw a second ago, if u is tangent, then that's u cubed plus u to the 5th du, which is then easy to integrate. So just let's work that out, see what happens. If u is equal to tan x, then du is secant squared x dx, and this is du. So the integral becomes u cubed plus u to the 5 du, which is easy to integrate. U to the 4 over 4 plus u to the 6 over 6. and u is tangent, so tan 4 x over 4 plus tan 6x over 6 plus c is the final answer. I'll summarize this when we get to the end, but just to say it one more time, this idea works if we have any even power of secant and then any power of tangent. Because we'll save 2 of the secants, convert the rest over into tangent by using that formula, turn it into a polynomial with a u substitution, u equals tangent, and then the derivative of tangent is the secant squared that we saved. So that will work with an even power secant and any exponent on tangent. Similarly, if we have a secant tangent that we can save, remember that the derivative of secant is secant tangent. So if we have something with secants, and then secant tangent as its derivative, we can make the same type of u substitution. So any extra power over here, right, so secant 5x, that will work because if u is secant, du is secant tangent, and it becomes u to the 5th du. So we get u to the 5th du, which is u to the 6 over 6, which is secant 6x over 6. Okay, so what do we do here? If we have a secant tangent and everything else is secants, then exactly that same idea will work. So how might we get to something like that? If we have an odd power of secants and an odd power of tangents, we'll be able to make that work. If I have secant cubed x, tangent 5th x, right, an odd power of secants and an odd power of tangents. What we're going to do is we're going to save the secant tangent, which leaves us with secant squared tan to the 6x. Actually, let me adjust what I just said. The secant actually can be any power. It definitely works if they're both odd. But the secant, let me just to emphasize that this is true. They don't have to be odd. Secant to 4th, tangent to the 5th. If we're still saving a single secant and a single tangent, the idea here is that, so that leaves me with secant cubed. Why is this okay, but we need to have an odd on tangent? We must have an odd on tangent in order to apply this rule, so that we're left with an even for tangent. Actually, if we do that, we'll end up with 3 of them still. 4. So that we end up with 4, an even number of tangents. Then we can use this formula that's up here to figure out, or to turn the tangents into a secant. But we need an even power on tangent so that we can apply that formula, convert them over to secants. Then I have stuff that's in secant and the derivative of secant. So that's why that will work no matter what the power is on secant, because that gets stuck down here and it doesn't matter, it's already in secant, which is what we want. But we need to have one of the tangents go over here as the derivative. The rest must be convertible back to secants. So we need to start with an odd, so we have an even here, so that we can use this formula. And let me just show you how that works. That is secant x, tangent x, secant cubed x. Tan 4, well, tan squared is secant squared x minus 1. And so if we square that, we get secant squared x minus 1 squared dx. And it looks complicated, but the idea here is that we have stuff that's in u. If u is secant x, then this is all a polynomial in u, and then this is du. So if u is secant x, du is secant x tangent x, which is why we took one secant and one tangent from our initial initial integrand. And then this is, the integral becomes, that's du, that's u cubed, and that's u squared minus 1 squared, and then du. This stuff here is du. Okay, it's straightforward from here, but I'll write it out. We do have to actually, in order to find this antiderivative, we need to FOIL, we need to distribute in so that our polynomial is easy to find the antiderivative of. But that's always the same idea. If we FOIL u squared minus 1, we get u to the fourth minus 2u squared plus 1. So that's just foiling that. Then du. And then we push the u cubed through, and I get u to the seventh minus 2u to the fifth plus u cubed. And then that's an easy polynomial to integrate. And we end up getting u to the 8 over 8 minus 2u to the 6 over 6 plus u 4 over 4. And finally return it to secant. Secant 8x over 8 minus 2 secant 6x over 6 plus secant 4x over 4. And we're done. Okay, so actually these are the only two types that we're going to worry about. Let me summarize what we found. What we found is that if we have a secant squared that we can change, or that we can save, and then turn everything else into tangents. So what does that really mean? If we need to be able to save a secant squared, turn everything else into tangents, so we need to have an even power of secants. If exponent on secant is even, right, then we save 2 and then turn others into tan x. And then let u be tangent of x, so that the derivative is the two secant squares that we started with. If exponent on tangent, this is the one that we just looked at, if the exponent on tangent is odd, that's the other idea that we just looked at. We'll save one secant and we'll save one tangent. So save secant x, tangent x. That leaves me with a even power on tangent. Use that formula to turn it into secant. Change remaining tangents to secants, and then let u equal secant x. So that's not everything, right? That's not every case. That's even on secant, and that's odd on tangent. But it could be that we're odd on secant and even on tangent. So that's the third case that we're actually not going to worry about. It's more complicated. It's not as straightforward to see what's happening. We have to use some other less obvious trig stuff and trig identities. So I'm just going to have you make sure that you understand how to do these two types. Just recognize that it's not exhaustive. There is a third option out there if you need to look at. But for this class, and these are the only two we're going to worry about. All right. See you next time.